Next speaker, Professor David Carfi. Subject: from Maxwell's equations to relativistic Schrödinger equation via Schwartz linear algebra and killing vector fields on the two sphere.
Thank you very much,
Please.
Chair, and thank you very much to the organizers for their great work in accommodate this magnificent conference. Thank you. So I'm sharing the screen, and I do not use the camera on me, and I'm sharing my work. Okay. So today I'm talking with Maxwell's equations, relativistic Schrödinger equation, or better equations, because we consider the massless equation and the massive equation, and all of this in the setting of Schwartz linear algebra in the space of temperate distributions, by using also the killing vector fields in order to associate with any temperate distribution representing a state of a quantum system, well, to associate a double vector field. In other terms, an electromagnetic like vector field. So our well, aim is to develop and to construct a mathematical structure capable to unifying scalar relativistic quantum mechanics and the classical electromagnetic field theory by means of Schwartz linear algebra. Indeed, well, the structure you will see in a few moments shall be the space S prime M4 C3. This is our space. Is the space well, of linear functionals from the test function space, the Schwartz test function space S M4 C towards C3. So we have a topology here, and the continuous linear functionals from here to the vector space C3 shall be our main structure. Well, S linear algebra, the Schwartz linear algebra, is capable to give some new operations in the space S prime M4 C, the space of temperate distributions defined upon the Minkowski space-time here and complex valued. Here we have, well, temperate distributions, but vector valued in the space C3. Okay. So we should embed the scalar psi belonging to our space of scalar states of quantum mechanics, standard scalar states, into the vector state space of electromagnetic fields or electromagnetic-like fields. To any psi belonging to a vast subspace of the space of temperate distributions, we shall associate a field F psi belonging to the space of temperate fields, complex three-dimensional temperate fields. You shall see how we will associate this vector field. In order to construct the embedding, we use a frame. We use an orthonormal frame upon the two sphere, and to any And in what space? In the dual space of Minkowski vector space, we have the space of wave vectors K. So a K is a wave vector, is an element of R3, and to each element of K could be also an element of the clearly I show you K is belonging to M4 star, is the dual of the Minkowski space, and K has two possible components. It has a time component, and it has also a special component. So we define our frame F on all this M4 minus a certain, singular plane, not so important, because, on the sphere, we have a polar issue. So the killing vector field, which is the first element of our frame R, the killing vector field continuous, cannot be defined on two polar points. And so we need to exclude all this line, because we extend this killing vector field to all the M4 star. And so we need to eliminate all this line. And we shall eliminate also the subspace in which K is equal to 0, completely equal to 0. So our frame is a frame indeed in R3 and in the three-dimensional space. And we have a bidimensional frame. We have two vectors. The first vector is a killing vector field, and the vector Sk shall be constructed by R. It is not this killing vectors field, but it is constructed by R in order that the three-dimensional basis Rk, Sk, and the unity vector of K shall be a right-handed orthonormal frame of, R3. So we construct this frame, which on the sphere is a tangent frame, in order to associate with any scalar state of quantum mechanics a certain psi, so an electromagnetic field. How to do this? So first of all, we consider the de Broglie basis. The de Broglie basis is a basis of temporal distributions. They are indeed regular temporal distributions, because we construct the eta k by means of smooth functions, slowly increasing at infinity. This is the Minkowski pairing, so is the Minkowski inner product. And I prefer to use this Minkowski inner product as a duality pair. So K is belonging to the dual of the Minkowski space-time, and X is the identity function on the Minkowski space-time. Well, the family of these waves, let me call it waves, the family of all these waves constitute a Schwartz basis of the entire space of temporal distributions. So we know that the family of all these waves, eta, generates by Schwartz. The span of eta is equal to the space, all space of temperate distributions based on M4. So, as we need in quantum mechanics, this basis, which is the so-called momentum basis, because any of each wave is an eigenvector of the momentum operator. So if you consider the momentum operator P and you apply to eta k, you obtain exactly the H cross, well, the H bar, and multiplied by k, the vector k, and multiplied by eta k. So eta k is an eigenvector, or if you want, an eigendistribution of the momentum operator P. And the eigenvalues are the de Broglie momentum pk, obtained by the wave vector k by multiplying times the Planck's constant. Okay, so we have to start from a basis of the entire space of temperate distributions in order to construct another basis. To be more specific and precise, we construct a Schwartz linearly independent system, a continuous system of vector fields, complex vector fields. These complex vector fields are constructed in this way. We multiply the element k of the de Broglie basis, so this temperate distribution, by a vector. This complex vector is obtained by summing the Killing vector field plus its companion sk times the imaginary unit. So we obtain this vector field, complex vector field, by multiplying an element of the basis of the temperate distribution space times this complex vector field obtained by a Killing vector field on the sphere, but we extend R to all the dual of the Minkowski space minus this singular plane by homogeneity. So in some sense, we construct an image of a basis of our scalar state space of quantum mechanics into a vector space of quantum mechanics, of Maxwell electromagnetism. In this moment is only the Maxwell electromagnetism. And the map is precisely defined as it follows. So we consider a scalar state of quantum mechanics, and we associate the superposition according to Schwartz. This is an integral in the sense of Bourbaki, if you want, or of Pettis, if you want. We consider this new linearly independent object, this one. So the family of all these vectors, Wk, and we superpose this family by using the, this is nothing but the inverse Fourier transform of psi, where the core or kernel of the Fourier transform is given by the de Broglie family above. So we use our new basis W. I can call it basis. It is not the basis of all our space S prime M4 C3. It is not a basis of all this space, but of a vast subspace of this universe. So I use this basis. I superpose with respect to this coefficient. This is a distributional coefficient, and I obtain my associated f psi. So, in order to fix the ideas, f psi, which is a tempered field defined on M4 and valued in C3, well, Fc is a superposition with respect to the dual of the Minkowski space-time, using this representation of the state psi, which is a scalar state in the basis eta, times the new linearly independent system W. And well, I should note that this is a scalar element. Literally is a scalar complex coefficient system, and this is the vector object which allow us to pass from a scalar state space to a vector state space. So we pass from the scalar to the vectors by means of a basis Rs, which is constructed starting from a Killing vector field on the two-sphere. Okay, I will show you the properties of this embedding. First of all, I should note that we can construct the momentum operator and the energy operator both on the scalar, well, standardly, the scalar state space of quantum mechanics, S prime and 4C, but component-wise, we can extend this momentum operator to the space, our new space, M4C3. And component-wise, nothing but an application of this operator to each component of our new objects. And analogously, we can proceed for the energy operator E. The interesting observation is that these operators viewed well, respectively, in this first space, scalar space, and in this second space, the vector space, well, commute, act compatibly through J eta F, in the sense that if I apply the J eta F to, well, a scalar psi, and I apply to this scalar psi the momentum operator P, well, I obtain the momentum operator P on the vector space applied to eta F of psi. So P, in some sense, is commuting, but obviously this P is not exactly this P, because this is the momentum operator on the scalar objects, and this is the momentum operator on the vector objects. But as you see, the embedding J is perfectly compatible with the momentum and the energy operators. Okay. And more interesting is the fact that if you multiply the operator curl, the curl operator times the Planck's constant, well, you obtain restricting to this subspace, you obtain exactly the magnitude of the momentum operator. So we have the momentum operator, the spatial component of the momentum operator, and we consider the magnitude of this spatial component. Well, we obtain exactly the Planck's constant multiplied by the cross, by the nabla cross, and nabla cross, which is the curl operator. So we, in this moment, are constructing a link between the quantum mechanics and Maxwell's electromagnetism. You can see it very simply, because if you apply P, the momentum P, to our eta k, eta k times R plus IS, you obtain exactly P WK. So you have that these objects we have constructed by eta k, are eigen distributions of the operator P. Okay, and you can see also that if you consider the momentum operator magnitude, and you apply to WK, you obtain exactly the momentum, the Broglie momentum under magnitude, and multiplied by WK. But on the space generated by W, so it is the, how to say, the huge space you can construct with the family W. You see, if you apply the H curl to WK, you obtain exactly the momentum, the Broglie momentum vector times WK. So this operator and this operator are exactly the same operator on the basis of this subspace. And so the restriction of this operator to the subspace S is exactly equal to H curl. So the principal operator of Maxwell's equations could be seen upon this subspace, could be seen as the magnitude of the momentum operator of quantum mechanics. Okay, we extend the theory, but I'm not interested in this moment. Let's go to the Maxwell-Schrödinger's equation. Okay, so in the space of scalar distributions, so the states of quantum mechanics, we have this equation, which is the Schrödinger equation, the relativistic Schrödinger equation for the photon. Indeed, if you remember, E equal Cp is exactly the relation for the photon in its energy. It's the energy of the photon by its momentum. And we can translate this relation, this functional relation, into an operatorial relation. Okay. The Maxwell's equations in our subspace S equal the span, the Schwartz span of W. In this space, the Maxwell's equations are, in a certain sense, change their phase. First of all, if I apply the divergence to our vector WK, the generating vectors, I obtain immediately, I obtain immediately zero. They are solenoidal vector fields. Okay. And so the first Maxwell's equations are, in a certain sense, already satisfied by the structure, the geometrical structure of our basis. Okay. On the other hand, we know that the other two Maxwell's equations can be seen as a Schrödinger equation. I will show you immediately, because we have dE over dt. This is equal to our curl applied to CB times C. This is the third Maxwell's equation. And the fourth Maxwell's equation, dCB over dt, is equal to minus, well, exactly the same relation with E. So we have these two Maxwell's equations. Okay, but I can write this in this form. So we have d over dt ECB equal the operator C curl applied to CB and minus E. Okay, well, you can immediately see that if you embed your ECB in our space as E plus ICB, you immediately see that this one is I times F. F is this one. So you obtain immediately that, minus I, obviously, and you obtain so immediately, one moment.
Professor, David finished?
Yes, I finish. I show you this relation and I finish. So you obtain that this two Maxwell's equations becomes I over dt f equal C nabla cross F. Okay, but this is the energy operator if you multiply times H. So you have here the energy operator, and here you have the momentum operator, because this is the momentum operator, times C. So you obtain again our formula, IH, so E, well, operator E, F equal to the C modulus P F. So the four Maxwell's equations are nothing more than the Schrödinger equation, the relativistic Schrödinger equation for the photon, applied to our new space of vector states. And this is the embedding of Maxwell's electromagnetism inside a space of quantum states. Okay, thank you very much for your attention. And
thank you for your presentation.